This is additive manufacturing lecture number 5, and it will be talking about. In the last lecture, we talked about the road mapping exercise and what kinds of road mapping exercises have been done for additive manufacturing. And in this class, we will be talking about the benefits of additive manufacturing, the differences between additive manufacturing and CNC machining, and we will also be talking a little bit about the very first technology that was developed for additive manufacturing, that is related to stereolithography. So, what are the benefits of additive manufacturing? The main thing is that there is a seamless transition from design to building. So, what you see is what you get. And in additive manufacturing, you can slightly twist that around and say that what you see is what you build. So, whatever you build virtually on your design space is what you will build, and it will help you to reduce the number of processing steps. And because most of the other manufacturing technologies require more than one step, here you only need one step. And of course you might need something like um, it will have uh, things like you may need to build support material, and you will have to remove the support material after the processing is done and so on. But in any case, the main difference between additive manufacturing and CNC machining is that CNC is primarily a subtractive process rather than an additive process, and it requires a block of material that is at least as big as a part that is being made. The current emphasis in additive manufacturing is, it is no longer a purely additive manufacturing technology. It is actually becoming a combination of additive manufacturing and subtractive machining, subtractive manufacturing, because most of the time what you get is you always do not get very good surface finish. So you need to have some form of subtractive manufacturing in order to get the right kind of surface finish for the ultimate part that is being built. Additive manufacturing initially was originally developed for polymeric materials, waxes, and paper laminates, but more recently there has been a lot of composites, metals, and ceramics being built by additive manufacturing. Um, Initially, it was just for form, fit, and show and tell, and it was only for making an intermediate part. And CNC works well with hard materials such as steel, metallic alloys, etc. And you know that additive manufacturing can result in part anisotropy, whereas CNC parts are more predictable in properties. So you may have to have some form of combination of uh, you'll have to have additive manufacturing, then some heat treatment in the process, then some machining, and so on, in order to get good uniform properties. The other major difference between CNC machining and additive manufacturing is that CNC machining is generally much faster than additive manufacturing, and it can add um, a similar volume of material, but the advantage is that additive manufacturing can produce a part in a single stage, whereas in CNC machining you require considerable setup and process planning, and in some cases it can even take weeks to make a part, whereas in the case of additive manufacturing it can produce parts in maybe a day or a couple of days, but it requires more time to finish the part for when you want to get dimensional accuracy and finish, you need to, it takes you time. So from a complexity of the part point of view, higher the geometric complexity, greater the advantage additive manufacturing has over CNC. And if you have some geometric features like accessibility constraints and things like that, or if you have undercuts, overhangs, etc., you need to have very careful process planning for CNC, whereas for additive manufacturing, these are not at all constraints. I mean, these are parts that can easily be built with using additive manufacturing. But what is the effect on accuracy? Additive manufacturing machines generally operate with a resolution of about tens of microns, and it can go higher. I mean, it can go better, but which means that your manufacturing times by additive manufacturing goes up exponentially. Whereas CNC, you can control the accuracy. Additive manufacturing can have variable resolution along different axes. So in the X and Y planes, it might be better, but in the Z plane, it could be pretty bad. And I mean, in fact, it can even be like, there will be a lot of ridges that are that you can observe, and it is not a good thing to have. But sometimes, what you will have to do is you will have to take it and you will have to hand finish it or do final machining and things like that in order to final grinding down in order to get the final surface finish. The accuracy in the build plane is going to be controlled by how well you can position the nozzle or the mechanism by which you are introducing the material onto the build plane, and it will normally involve stepper motors and gearboxes and things like that, and that will control the cost of the additive manufacturing machine. So if you go and buy a $300 machine from Staples, it is most probably going to have stepper motors that cost about $5 a motor from China. Whereas if you buy an additive manufacturing machine that costs, say, $300,000 or $400,000, those stepper motors are going to cost maybe like $1,000, $2,000. So that's going to be more accurate than a $5. Obviously, it's going to be more accurate than a $5 stepper motor. So that is going to determine the final cost of your additive manufacturing machine. And it will also determine the minimum feature size. In the case of stereolithography, SL stands for stereolithography. It uses a laser as part of the build mechanism. So that is going to be controlled by galvanometric mirror drives. And the resolution of that would determine the overall dimensions of the parts being built, while the diameter of the laser beam would determine the minimum wall thickness. So suppose your laser dimensions are going to be in the millimeters. You can only, you might need to have at least 3 of those lines put together in order to get some reasonable strength for your wall. So that's going to be, so your wall thickness has to be minimum, say, 3 millimeters. Whereas, if your laser dimensions are going to be of the order of, say, maybe like tens of microns, then your wall thickness can be probably like, maybe millimeter or 2 millimeters and things like that. So that's going to determine the minimum wall thickness. It is also going to be determined by the positioning resolution along all the three orthogonal axes and the diameter of the rotary cutting tool. Suppose you have rotary cutting tools that are going to be part of this machine, that is also going to control the final part dimensions. So very fine detail is going to be controlled by that. But what is also important to note is that it is also a function of the build material and the support material. Essentially, what are you doing? You are essentially breaking up a 3D problem into a series of 2D cross sections with a nominal thickness. And the connectivity between the different surfaces in 3D is removed, and how close you can make the cross sections with an adjacent one is going to define the final dimensions and final properties of your component. In CNC, the main difference is that your surfaces is generated in 3D space, so you can have curvatures and things like that. Whereas, and if you have very simple geometries like cylinders, cones, etc., this is pretty easy. But if you have free-form surfaces, there can be a lot of changes in orientation, and it can become extremely difficult with CNC, even with 5-axis control. So you need to have, so your cost of your CNC machine goes up exponentially. And if these features are beyond a certain limit, then undercuts, enclosures, sharp internal corners, etc., are all going to be difficult to machine. And you need to be able to manipulate the component as well as the axis that is going to be doing the machining at the same time. Is that going to be easy? No, not at all. And that's probably going to be taken away when you are doing additive manufacturing. So take the example of a simple cup. Now, it could be cast, but if you are going to be doing machining of this kind of a component, the base cannot be machined because the machine must also hold using a fixture. You cannot have sharp internal features without a tool radius, and you cannot have undercuts without more than 3-axis machining. And sometimes how deep it is also going to control how well you can machine this part, because in this case the cavity here might be too deep for you to machine that. So if you want to make it by additive manufacturing, you can do that, but by CNC it is almost next to impossible to make. The other thing that you need to note is that when you are programming a CNC machine, it can be extremely involved, like how the tool is selected, how the machine speed settings. So you have to have freedom. I mean, like we want to have the freedom to design all that or define all that during the manufacturing design process, during the design process. But that also can work against you because you are taking away the knowledge of the machine. So if the machine can define how the part is going to be, that's going to be difficult. And the range, complexity, and implications in additive manufacturing are pretty minimal in comparison compared to CNC machining, and this can be done pretty easily. But sometimes what happens is that the machine can go crazy while you are building it by additive manufacturing. So the part may not be built properly because the axis of your deposition head can give you nightmares. So sometimes the part may not build properly, whereas in the case of CNC, the tool can foul against the part and it can damage the machine and it could be a safety hazard. So if your machining tip is pretty sharp and if it breaks and it can just go like a boomerang, I mean not a boomerang, like a bullet, and it can hurt people around. So you have to have pretty stringent safety features built into the CNC machine, whereas you don't need to do that in the case of additive manufacturing. So uh, these are some of the things to uh, understand, and there are some related technologies that I want you to understand. First one is reverse engineering. Where does reverse engineering come into place? Reverse engineering comes into place especially when a part doesn't have a drawing, or you're trying to build a part, say for example, a part for an antique car, or a part for which there is no machine drawing that exists. I mean, this part has been around for, say, 60 to 70 years, and now you are suddenly having to build it again. So how do you do that? So you take or for example, a broken bone. Um, so you can't take it from a series of drawings or from a set of drawings. You have to create it from scratch. And sometimes all that you have is a broken part. So you take that broken part, somehow fit it all together to somehow simulate an unbroken part, and then you laser scan it, and take the data, cloud data, and create an model that the machine can use to build the part. So that is called reverse engineering. CAD, obviously, you know. And the other one is called haptic based CAD. And so you are bringing in some kind of knowledge based system in order to, I mean, suppose, you as a designer say that, hey, this is how it should be built. But the machine, from its knowledge of the materials as well as the machining process, it says, no, that's not the way to build it. You will have a problem. So we should go ahead and build it by slightly different ways. So that's where haptic based CAD is going to be the case. So reverse engineering is the process of capturing geometric data from another object, a broken part, and it is available in what is called point cloud form, and it is an unconnected set of points representing the object surfaces. So you are only going to get the surface and not what is inside, and you will have to define that by manipulating the data and creating the CAD model itself. And it needs to be connected together using reverse engineering software. It's called GeoMagic, and I believe that this company that is making this software is from Europe. They are called Materialise, Materialise. I would suggest to you that you should go in and do some checking to find out what kind of reverse engineering software is available and how do you define the final part to build. And it can be used to combine clouds from different scans, and it can also perform other functions like hole filling and smoothing. And in any case, the data is not going to be entirely complete. So you have to manipulate the data, and that's going to give you the final component. One thing to note is that when you're taking a broken part, it needs to be placed in a holding fixture. So sometimes, you don't want to scan the whole thing. And so some of the surfaces adjacent to this fixture may not be scanned. And also you may have some surfaces that can kind of prevent you from scanning other areas, like if you have deep holes and things like that, or you have internal features, you may not always see that in this scan, and it may not turn out exactly how the object is in reality. So you have to go back and manipulate this data. So it's usually done by laser scanning or touch probe technology. And you can also do CT scan. So CT scan can do take the MRI data, create MRI data, and the MRI data is going to be manipulated to form the final part to be built. And then once you have the final data, then you have final design, you cut that into layer by layer software, and use the materially software to join these layers and identify the surface boundaries. And once you have been using this for a while, you get very familiar with what needs to be done. And then the first time you do it, you're probably going to make a lot of mistakes. The second time and third time, fourth time, fifth time, you are definitely going to be much more accurate with this data. If you are having CT scanning, then you can generate the internal features. And if you have industrial technologies, then you can also do high energy X-rays to create high resolution images of around 1 micron resolution. So that's all going to create that. So how do you do this? You first capture the geometry inside. Then, say for example, if you have reverse engineering inside, you can digitize the objects. Then you can do cross sections, 2D imaging to capture the cross sections of a part as it is machined away layer by layer. In some cases, you may destructively remove destroy the part in order to make the final design. How do you do reverse engineering in medicine? I talked about it in one of the first lectures, and you take the individual patient data with an engineering design to form a customized medical implant. And that's, or if you scan the left leg and if your right leg was broken, then you have to reverse that, or you have to mirror that in order to get the final part. You can also do 3D CAD, if you have to build the design, and it is an extremely valuable resource for product design and development, and it helps you to implement the change easily and cheaply, because if the design is in a software format, then you can make those changes very effectively in a very quick manner. You can also link that with other softwares like finite element modeling, or other, thermal analysis and things like that. And it can help you to determine the forces, stresses, flow, and other properties to determine how well a design will perform under certain conditions. And it is a cost-effective solution for you. Haptic CAD is something that has come on board very recently. It provides a mechanism for greater freedom of expression, and it is becoming a popular tool for artists and sculptors, because most of the computer-based design tools constrain or restrict your design. And if you want to make something that gives you that freedom, there is a scope for a CAD system that provides that kind of an approach. So these are some of the pictures of how a part is built. So you can say, for example, you can do a touch pen and you can touch the surfaces and it automatically transfers those XYZ points to your design inside your computer, and you can create the CAD model for the part that has to be built. In this case, the haptic CAD is this. I mean, suppose you want designs like this, you can't do it any other way. So again, these are some of the associated technologies, and you have to create or you have to use layers as a way to form a 3D object. I mean, that's the only way to use additive manufacturing. So you need to understand the effect of doing that. So how does the final part that is built by additive manufacturing relate to how you have designed the part in additive manufacturing? So you need to be able to orient that part in your build envelope. You need to be able to build up the supports, and then after the part is built, you need to figure out how to remove those supports. And then sometimes you may not be able to build hollowed out areas, so you may have to do that afterwards. And how do you include undercuts and other manufacturing constraining features, etc., is going to control your final part that is built by additive manufacturing. So just to start out, we will talk about photopolymerization. Photopolymerization is a process that is used in the stereolithography process. And here we are using a liquid radiation curable resin or photopolymers as the primary materials. And they react to radiation in the UV range of wavelengths, but sometimes you also use visible light. And once you irradiate them, they undergo a chemical reaction to become a solid. And this reaction is called photopolymerization, and it is a pretty complex chemical process. You can have different kinds of radiation for photopolymerization, like gamma X-rays, electron beams, UV, and sometimes visible light. And in the case of stereolithography systems, UV and visible light radiation is the one that is most used. The others are definitely not used, because you will need a lot of protection in order to be able to use those kinds of radiation. So how do you do that? You have a vat of material where you have a resin, and you have a laser beam that is being controlled by a computer, and it will scan that first top layer in the XY plane alone. Then um, the platform will shift down by a small amount. Then more resin will pour over your sample, and then the laser will scan the surface, the areas where you need the part has to be built, and it will keep on doing that till your final part is built. You can have two ways of doing this. One is by mass projection or layer wise. So you irradiate the entire layer in one shot, or you can have point by point approach to irradiate the resin layer. So this is a schematic of the process, and how it is controlled, the movement of that is controlled by using what is called a galvanometer. The galvanometer will sense the height from which the radiation is being beamed, and it will control how well the part is built. So in the case of the mass projection, you are using what is called a digital micro mirror device. In in the case of the two photon case, you have two scanning laser beams, and they intersect with each other in order to get the maximum radiation power. In the case of the vector scan and mass projection, there is sometimes the need to recoat or apply a new layer of resin. Uh, Whereas in the case of the two photon approach, the part is fabricated below the resin surface, which makes recoating unnecessary. The approaches that avoid recoating are faster and less complicated. So the two photon approach is a faster process. So what is the structure of the photopolymer that is being reacted with the UV light or the visible light? They are acrylate resins, and they were originally patented in 1989 and 1990 by Ciba Geigy. I'm sorry, there is a lot of write-up here, but essentially these acrylate-based photopolymers are highly reactive, but they can produce weak parts, and what you will find is that they complete only 46% when the part has been, the image has been transferred through the laser. I'm sorry, there is a lot of writing here, but what you're doing is you're essentially uh, curing each layer, and once the laser beam hits the resin, it also partially cures more the layer that is directly beneath the layer that is being cured. So that is going to give you some kind of shrinkage as well as heat generation and things like that. You're going to have some amount of shrinkage. So that shrinkage can vary from 5 to 20%. But that shrinkage also gives you excellent addition and reduced tendency to for those flexible substrates to curl during the cure. So what I would recommend is that please look up the Rapid Prototyping Journal and some recent articles on photopolymers, and you can look at the um, patent literature for the original Ciba Geigy patent that is from 1995. I would like you to figure out the applications of stereolithography and write about half a page to one page article on why stereolithography is still a good process to use, and how it can be used for fabricating patterns for investment casting of metal parts or for injection molding parts. That's all I have for this lecture, and I'll be posting this lecture in the next hour or so. It might take me a couple of hours to upload that, but hopefully I'll be posting more lectures that made me miss the earlier um, sorry, uh, I lost my chain of thought. I apologize. So what I want you to write is a half a page write-up on why it is a good process and how it can be used for making different kinds of parts. And what I would also recommend is this. Stereolithography also has been used by people from University of Michigan to make ceramic parts. And the person's name is John Halloran. I would like you to go and look up his name and stereolithography of ceramic loaded resins, and it'll give you some ideas about how this process has been leveraged to make parts for other processes. So anyway, that's all I have, and I'll stop here. Thanks.